students, welcome back. Today we are going to start with chapter 2, atoms, in our lecture. So in this chapter, we are going to learn things about the concept of atom and how did it develop from the ancient Greeks idea of the matter. And then we will go ahead and describe the significance of laws of conservation of mass and definite proportions. We will dig in deeper to learn and calculate the amounts of elements from its composition, explain why the idea of matter is made up of atoms is a theory by using Dalton's theory, and by using Dalton's atomic theory, we will also learn to explain the laws of multiple proportion and conservation of mass. Then we will go ahead and learn about mole and how is that used, convert between masses and the moles of the substances, and we will wrap up with learning about how the elements are arranged in a periodic table and why that arrangement is important. You will also be able to distinguish between atoms and molecules by the end of this chapter. Hear about atoms almost every day, but are they for real? So in about 20th century, we started seeing the beginning of so-called atomic age, and the terms atomic power, atomic energy are a part of our vocabulary. But what are these atoms? So atoms are the building blocks of matter, and why do we care about them? Because they control the behavior of all matters. So the atoms, everything, every material thing in the world, including you and me, is made up of atoms, and atoms determine how this matter behaves. So we are in a chemistry course and we are learning how to study the behavior of matter. It is necessary for us to learn about atoms to gain more insight into how everything works. So the concept of atom was first suggested in ancient Greece, and in the Greek philosophy, all matter was considered to be composed of 4 elements as shown here in the figure: air, water, earth, and fire. And Aristotle, who was a popular Greek philosopher, his view of matter was that all matter is continuous and not atomistic. However, Leucippus and Democritus, they made an observation, and they believed that matter, or the tiny particles that they called atomos of water, could not be divided further. So atomos, according to them, was a point at which matter can no longer be subdivided. However, their idea of atom was rejected for almost 2,000 years in favor of Aristotle. Democritus, he continued or expanded on the Leucippus idea of matter, where he believed that atom was distinct in shape and size, and in this picture here, as shown in this picture here, he imagined that the atoms of water might be smooth and round balls, like shown here, and fire, which can burn or which might have sharp edges. So they continued with this idea of atomos, meaning which cannot be cut any further. So let's practice a question like a question on what we learned so far. So the term atom comes from the Greek word atomos, which means, so pause the video, look at the options, think what we learned, and then select the answer. So now in this portion of the chapter, we are going to talk about scientific laws. We are going to talk about conservation of laws of conservation of mass and definite proportion. We will learn about these laws, and we will also learn to do problem solving based on these laws. So, so as we looked at the historic perspective, a little progress was made in chemistry, especially the atomic view, until about 1700s. And then after that, a lot of discoveries were made, and it was a beginning of modern chemistry, as we know. And here, let's take a look at the law of conservation of mass, which was devised like in early 1700s by Lavoisier. He summarized his findings about the total mass of reactants and products. So what does the law of conservation of mass say? So, so during a chemical change, matter is neither created nor destroyed. That was the summary of the law of conservation of mass. And Lavoisier is considered by many to be the father of modern chemistry. Example or demonstration of law of conservation of mass. In the figure here, you can look at the decomposition of mercuric oxide, which is a reddish colored solid here. On decomposition, it produces mercury, shown here in the gray color in this bottle, and oxygen, which is depicted by this balloon. That balloon is filled with oxygen, a colorless gas. Mercuric oxide has none of the properties of mercury or oxygen, because look visually, you can look at the colors. Mercuric oxide is red solid, mercury is gray liquid, and oxygen is a colorless gas. Now, so although the properties are not the same, or the properties of mercuric oxide are completely changed in the reaction, let's look at their masses. So there are 100 grams of mercuric oxide, which decomposes to form 92.61 grams of mercury and 7.39 grams of oxygen. So it tells us that the mass, there is no change in the mass, or the mass is being conserved in this change or in this decomposition reaction. So in this chemical change, irrespective of the change, the matter is neither created nor destroyed, and the mass is conserved. So the grams remain the same. So let's look at an example to practice this law, practice what we learned. So there are 4 grams of hydrogen that reacts with 32 grams of oxygen to give you 36 grams of water. And the question is asking you what law is being illustrated. So 4 grams of hydrogen plus 32 grams of oxygen is giving you 36 grams of water. So even if you don't know the formula for hydrogen or oxygen, just by looking at the masses, you know that 32 plus 4 is equal to 36. So which law comes to your mind? What is being illustrated here? So you know that it's a law of conservation of mass, because the mass is conserved in this reaction.